Okay, so I wanted to make a couple of announcements before starting. There is an exam on Wednesday, as you all know. And because there is an exam, I'm not going to have the class in the morning. Okay, the exam is an evening exam. There will be no class, and you can use the class time to come see me. I will have office hours as well, and you can use the class time to come talk to me if you have any questions about the material for the test. So you can use that as extra office hours. Okay, so feel free to stop by on Wednesday, or if you need to come talk to me some other times today or tomorrow, email me and I can see if I can allocate a time. Okay, so review all of the material. Start with the lecture slides. Okay, don't start with the book and start reading 300 pages of the book. That is not a good strategy. Okay, I'm only going to focus on what we have covered in class. There is material that is in the book that we did not cover. You do not have to be responsible for knowing that material. Okay? Only things we have covered in class is what you need to really know. Okay? So start with the class slides. There are some notes. All the videos are there if you need to go review the material, and if you still need to come talk to me and understand some concepts, please feel free to stop by. Okay. Any questions about anything about the exam? I put up a sample midterm from last year on Moodle. Okay. I hope you have had a chance to take a look at it. That should give you some sense of what the exam typically looks like. Okay. So take a look, see if you have any questions about that kind of material. Okay. Obviously, those questions will not appear on the test. So, yes. Any questions or comments? Okay, so just keep in mind, don't come to class on Wednesday because we will not have a class. Okay, that's really the thing to keep in mind. So what I'll do today is just continue the discussion that we had started last time on distributed snapshots and whatnot. So just from the exams perspective, everything we covered until last Wednesday will be on the test. Okay? Today's material is not going to be on this test, it will be on the final. Just to give you enough time to study, I didn't want last minute material to be part of the test. So whatever I say today is not going to be on this test, it will be part of the final, but do pay attention in any case. Okay, so what we will do is talk about distributed snapshots, which is what we were discussing last time. Then talk about termination detection, which is a variant of distributed snapshot. That's another problem, okay, in distributed systems. Then I'll talk about, spend much of the class talking about this problem of leader election. Okay? This is the problem of finding a coordinator to help with any distributed systems problem. We'll see how to perform leader election. And I'm going to probably get to this towards the very end. This is going to be how do you do distributed locking, okay? Distributed mutual exchange. So we are still going through a set of these canonical problems. We have finished clock synchronization, we have finished logical clocks, we looked at vector clocks, we were talking about distributed snapshots. Okay? Just as a recap, we said that the global state of a distributed system, which consists of n processes, is the local memory state of each process and all of the messages that are in transit. Okay? If you capture all of the memory states of the processes and the messages in transit, you have captured what is called the global state of a distributed system. Okay? And I was talking about this notion of taking a distributed snapshot, which is a consistent global state. If you have any problems or failures with any of the processes, you can terminate them all. You can restart all of the processes in your system from your distributed snapshot, and that will allow you to consistently continue forward, making forward progress. Okay? And then the question was, how do you take a distributed snapshot in a scenario where there is no clock synchronization? Or I shouldn't say no clock synchronization, there's no global clock. Okay? So if you had a global clock, you could take a snapshot at precisely the same time in all of the processes, but you do not have that luxury. So now we need to figure out how to solve this problem without without assuming the clocks are synchronous. And I did mention this notion of a consistent cut and an inconsistent cut. And basically, what you want to do is take the memory snapshot of each process. Okay, that is an easy part. But then the question is, how do you define what are the messages in transit? And essentially, what you want is to capture all the messages that have been sent but not received, and that those are the messages in transit. So you do not want to ignore any such message. Neither do you want any message to be duplicated. Okay, so those are some of the issues we need to worry about. I'm going to talk about the algorithm now, but let me see if there are any questions. Is the problem clear? What is a distributed snapshot? If you don't understand the problem, the solution is not going to make sense, obviously. So first question is it clear what we are trying to do? So we have n processes. Okay, we assume that processes can fail, and if they fail, then you don't want to terminate all of the processes and restart them from the beginning. That will waste all of the work that they have done. Instead, what we want to do is periodically checkpoint the state of the system, which is the global state, so that if any process fails, you can terminate them and restart them from the most recent checkpoint, which is our distributed snapshot. Yes, question. Okay. What's the question? Oh, you want me to explain consistent and inconsistent cut again? Okay. So, this was at the very end of last class. So as I said, if you had a global clock, okay, which assumes that every clock is perfectly synchronized, one way to take a distributed snapshot is to tell all processes saying, let's say at some time noon, every process freeze, or at the end of each hour, every process should freeze. Okay? At that point, you will basically have each process write its memory state to disk. Okay? You will also look at all the messages that are in transit that are sitting in some socket buffers. You will copy those messages also to disk, and you would be done. If you had this scenario, what would happen is this dotted line, wherever it intersects the processes, is the point in time where that process takes a checkpoint. Okay? So if you had a perfectly synchronized clock, the dotted line would be a straight line, so everyone would actually freeze at exactly the same time and take a snapshot. Okay? That is by definition consistent, because in that case you are a consistent snapshot. Okay? So that's the first trivial example of how to make a consistent snapshot with a perfectly synchronized clock. But in the real world, clocks are not perfectly synchronized. So if this is real time, they are sort of taking snapshots at the same time, but some clocks are so slow, some are fast. So what is actually happening is this process takes a snapshot at this point, this process takes a snapshot of this time, that process is running slow, it takes a snapshot a little later. And then the question is, how do you ensure in such a scenario that your snapshot is consistent? Okay, and now our definition of consistent is that what you want is when you take a snapshot, whenever a message crosses this dotted line boundary, what that essentially means is the send of the message has preceded the snapshot and the receive of the message is after the snapshot. Okay, so this is M3 is an example where the send is before the snapshot because this process took its snapshot here. So it has already sent the message. Okay? And this process P2 has taken a snapshot here at this point in time. That message M3 is received sometime in the future. Okay? So that is a message in transit because the send has occurred before the snapshot, the receive is going to occur after the snapshot. So what we want in a consistent cut is to actually capture all of these messages because these are called messages in transit. Okay? Because if you restart the process, the send is not going to happen again. The process is going to restart at this point. Okay? So you somehow need to have taken all the message buffers and also reinsert the message into the buffer so that it will be delivered to P2 and P2 can process it at some later time. Okay? So a consistent snapshot, essentially what this is saying is consistent snapshot is one where all the messages in transit are fully captured. Okay? M1 doesn't need to be captured because M1 has been sent and received before the snapshot. Okay? So it's on the left half of the snapshot. M2 doesn't need to be captured because M2 is actually now neither sent nor received when the snapshot was taken. So you don't need to worry about these messages. What you do need to worry about is messages like M3. Okay, so now the question is, how does the snapshot become inconsistent? Here is an example of what has happened with an inconsistent snapshot. So again, if you say assume the clocks are not synchronized, the dotted line shows you when the processes take the snapshot. Wherever the dotted line intersects with the process is the time it has taken a snapshot. Right? So now in this case, what happens is the send of the message occurs after the snapshot and the receive of the message has occurred before the snapshot. Because the receive is before, in this case, the send is after. So if you now capture that message, okay, you will have inconsistencies, because what will happen is P2 will restart at this point, it will continue execution forward, and it will resend M2. Okay? But M2 has already been processed by P3 because it has actually taken a snapshot after M2 was processed. So if the message is sent again after the processes are restarted from a checkpoint, M2 will be sent twice. Okay, so this is inconsistent because you basically have the same message being processed twice. So you don't want that scenario. So in other words, you don't want a scenario where the receive is on the left half and the send is on the right half, because in this case, looks like this receive has happened before the send even happened from a snapshot's perspective. That is inconsistent. Okay, this seems a very straightforward observation, but you don't want this. Okay, this will result in duplicate messages being delivered to the application and messages getting processed twice. So if the message was add $100 to an account balance, you will process it twice and you have inconsistency. So you don't want that. Okay. Question is, how do you take an inconsistent snapshot? That's the algorithm we are going to look at. Okay. Any questions about this? Okay, so you neither want to lose messages in transit, neither do you want duplicate messages. That if you do achieve those two goals, then you will have consistent snapshot. All right. Okay, so here's your distributed snapshot algorithm. So we are just going to assume processes communicate with one another with TCP, over TCP. Okay, so we will not worry about network lost message or anything like that, because TCP will retransmit. So essentially we will get in order. So TCP gives us several properties that we are going to depend on. Messages are received in the order in which they are sent. TCP guarantees that for us. Okay? If you send message A followed by message B to another process, that's the order in which TCP will deliver it. Okay, if you receive them out of order, it will buffer them and deliver them in order. So we'll assume that the channel is ordered, okay? Meaning that when I send messages, they appear in the same order. The messages won't hop over one another. So simple TCP channels will give us that, okay? And there are no losses involved. So we'll make that assumption that all processes communicate using TCP and not UDP, for example. Now the algorithm is very straightforward. I'm going to show you, this is the description of it, but what I'm going to give you is a pictorial description. So we'll assume that any process can initiate the snapshot algorithm. Whenever any process out of these n processes in the system feel like it's time to take a checkpoint, they will just start the algorithm. Okay? And what do you do when you start? You basically, whenever a process starts the algorithm, it will first take a snapshot of its memory and write it out to disk. That's called a checkpointing local state. Okay, that simply says you freeze temporarily, okay, take the memory contents, write it out to disk, okay, and then resume. Okay, so that's capturing memory state. And now, since you also have to capture messages in transit, we'll have to do a few other things. Okay, for what we will also do is send a special marker message on each of the outgoing channels. Every process to which I have an active socket connection among these n processes, okay, are the ones with which I have an outgoing channel. So on every TCP connection I have open at the moment, okay, you will send a special message. Okay. The special message is called a marker message, and the marker message simply says start recording. Okay. So this is how you start the algorithm. Any process can start. Right? Once you decide that it's time to check a checkpoint, you take your copy of your memory, write it out to disk, you send marker messages on every outgoing socket connection. Okay, very straightforward. And now what do other processes do? On receiving a marker, so there are other processes to which the first process has sent marker messages. Okay. So now let's consider the case where a process has received a marker message. Okay, that's this scenario. So upon receiving a marker, okay, so basically you will say, okay, some process has started a snapshot algorithm, so you will immediately write your memory state to disk. Okay, so you are going to copy your local state. Okay. Okay. And then what you do is you are going to start recording all of your incoming channels, okay, saying those are messages in transit, and you send markers on the outgoing channels. Okay, so checkpoint state, if this is the first time you receive the marker, send markers on the outgoing channels and start saving messages on all incoming channels until you receive a marker on the incoming channel that says stop recording. Okay, I'm going to show a picture that will make this easy. Okay. And then you finish whenever a process receives a marker on all of its incoming channels. So let's take an example and work through this so you'll understand what's going on. I'm going to assume that there are 3 processes. You can make 4 if you want. Okay, so I'm going to draw bidirectional channel just to show what's happening. Okay, so we have a system of 4 processes A, B, C, and D. A has active socket connections to B and C. C has an active socket connection to A and D. Okay, that's the scenario. Okay. So we'll assume that now you want to implement distributed snapshot. So any process can start the snapshot. For simplicity, we'll just assume A starts the snapshot. Okay, so we'll just work through the algorithm. Okay, so what A will do is it will write out its memory content to disk. Okay, so it's going to do that, and then on each of the outgoing channels, it's going to send a marker message. Okay, and at the same time, it is going to start recording every incoming packet that's coming in. Will on its incoming channel will start getting recorded. Okay, to disk. So if there are packets coming here on the incoming channel, a copy of each of these packets is going to be stored on disk. So these are the socket queues. Okay, is that clear what I said? Okay. So now B is going to, let's say, receive, let's start with C. C is going to receive the marker message that was sent from A, and when C receives the marker message, it's going to say A has initiated a snapshot, so time for me to also do the same thing. So what C is going to do is it is going to write a copy of its memory content to disk. Okay, and it's going to send marker messages on all its outgoing channels, and it's going to start recording its incoming channels. Okay, so it's going to send a marker here, going to send a marker here, and any messages that are coming in are going to be recorded. Okay, and this is going to recurse. Okay. Now each process will stop recording its messages until it receives a marker on that channel. So for instance, A was recording all the messages that C was sending to, but then there's a marker message that C sent. So these 3 messages will get recorded. When the marker message comes, that's going to say stop recording. So marker message indicates either start recording or stop recording, depending on whether it's the first one or a subsequent one. Okay, the very first marker message says start recording, and then when you start receiving all marker messages from your incoming channel, that says stop recording. Okay, and then the claim is those are all the messages in transit. Okay, why that is the case we'll start discuss, but first let's make sure you understand the algorithm. Any questions on this? First, what the algorithm does? Okay, so each process can start, or any process can start. Once you start, you copy your memory contents to disk, you send marker messages on all your outgoing socket connections, and you start recording all the messages that are coming on your incoming socket connections to disk. Okay, those are all messages that will have to be reprocessed should the process have to be restarted. Okay. The first time any subsequent process receives a marker message, you record your own memory contents to disk, and you do the same thing. You send markers on all outgoing channels, you stop, and you start recording all incoming channels. And you stop when you received a marker message on the another marker message on your incoming channel. Okay, that's it. That's all you need to do. Okay, and the claim is this is going to get us a consistent cut. Why that is we will talk about. Okay, does anybody have any questions on the algorithm? Okay, now we should look at this carefully and try to understand a few different things. So let's look at this a little more carefully here. Okay. So let's take C, okay, which has received this marker message, which I'm going to make it red here. So that's the one you sent. The one So C receives its first marker message from A. Okay? At which point it starts, copies its contents to disk and is going to send a marker to D and a marker back to A. And it's going to start recording its incoming channel. So I said, for instance, all the packets that are coming from D are recorded. Okay? The question is, should it also record any more packets that A sends? In other words, should it record anything that comes after the marker message, which are packets shown in green? That's an incoming channel for C. Okay, you shouldn't record, is some what people are saying, and why is that?
Because A has already saved its state.
Okay, A has already saved its state. Any other comments? Why?
In case we go back to that checkpoint, A will resend those messages.
Okay, so as is being pointed out, the marker, when you receive a marker message on your incoming channel, it says two things. It says start recording, but for that channel, it also says you're done, stop recording, because you already received a marker on that incoming channel. For any other incoming channel where you have not received a marker message, you start recording your messages. So in particular, if you look at the scenario with C and D, C sends a marker to D, at which point D is going to write its state to disk and then send a marker back. Okay? So all the messages that preceded the marker message will be written out. Okay? And you stop recording when you receive this marker message. Okay? From A to C, the marker message that A sent is enough to say start recording and also stop recording. There's no subsequent markers that are going to come from A. Because A is already snapshotted its memory. Okay? So you need to distinguish between the first time you receive a marker message on your incoming channel and all the subsequent times you receive marker messages on your incoming channel. The very first marker message tells you to snapshot your memory. Okay? And it also says that there is no reason to record on that channel anymore because you already received the marker message. But all other socket connections you have to record until you actually receive a marker message. So you have to distinguish between these two cases. Okay, so that's one. Second question I would ask is, are we guaranteed that this algorithm will actually end and there's no infinite loop where markers are going to keep coming back and you're going to keep doing this thing all over again? Okay, so for example, C has sent a marker back to A. Okay. What if a marker goes to some processes and then it flows back after some number of hops? Okay, will that cause some sort of an infinite loop where the algorithm just keeps doing the same thing over and over again? Thoughts on this? The algorithm end? Yes. He's confident it's going to end. Why would it end? So you can ask yourself a very simple question. If a process has already taken a snapshot of its memory state and it receives a marker message subsequently from some other process, what does it tell that process? Okay, all subsequent messages only tell you to stop recording, not that you have to start taking another checkpoint. Okay, so if by some chance there was a C and there was an E, and then E sent a marker back to A, all that is telling A is that just stop recording on the channel. It doesn't say restart the snapshot algorithm. So beyond the first marker, okay, all other markers only tell you to stop recording, which means the algorithm should terminate. Okay, it shouldn't cause you to restart taking snapshot. It's a very simple observation that just because you get more markers down the road doesn't mean you're going to be in a loop. It's only telling you to stop, not to restart. So you will interpret it properly and eventually the algorithm will stop. Okay? But then that also begs the question, will you actually receive markers on all of your incoming channels so you will stop? Another way to not stop is that you keep on recording all of your socket messages and you never stop. Okay, so what do we know here that will tell us that you will actually receive a marker on each incoming channel that will tell you to stop recording? Minor detail.
Can you repeat the question?
Sorry?
Can you repeat?
Oh, I can certainly repeat the question. So we already said that if you receive subsequent marker messages, that they will not cause you to go into a loop. That's good. Okay? But then the other way that the algorithm can never stop is, I said, once you receive a first marker, you snapshot your memory and you send markers on all your outgoing channel and start recording your incoming channels. Okay? And then the question is, and then you will have to wait for a marker on the incoming channel that tells you stop recording. Now, question is, what is the guarantee that you will actually receive a marker eventually on your incoming channel that you will stop? Okay, what if you never receive a marker on some incoming channel and you keep recording forever?
Just use TCP.
Yeah, so there's no network losses. Okay, so let's ignore that case. So you're saying this because it's TCP you're guaranteed to receive it? Is that what you said? Okay. Why is that? So first we are going to assume this connected graph. We have some process that doesn't have a socket connection with the rest of the system. That process will never receive a message. So let's ignore that. So we'll take all the processes that have some connections open and we'll take the graph. Okay? Take any two arbitrary nodes in this graph. Okay, let's take node I and node J that have a socket connection open. Okay, so one of these processes is going to receive the marker message for some other process that started the snapshot, and eventually the markers are trickling and one of them is going to get it first. Okay, and that's the one, let's say J receives it first, it's going to send a marker. Okay, if J sends a marker to I, okay, if it's the first marker, then I will actually take a snapshot and send a marker on the outgoing. So then basically I's outgoing channel is J's incoming channel. Okay, so if J sends a marker to I will at least cause that marker will at least cause a marker to come back in the opposite direction. Okay. The only other case is I not only receives this marker from, it also receives a marker from some other process K that arrives at I before this one, and in that case also you are fine because I will snapshot its state and send a marker on the outgoing channel. Okay. So long as every process receives a marker, it's going to send it on its outgoing channel, and because all TCP connections are duplex, someone's outgoing channel is someone else's incoming channel, so it follows that you will always receive a marker on an incoming channel and you will always send a marker on your outgoing channel. So this should cause everyone to stop recording. Okay, either it's the first marker or it's a subsequent marker. In both of those cases you will be done. Okay, so the algorithm will not just keep recording forever. This is not a formal proof, but you get the intuition as to why the algorithm will actually finish. Any questions here? Yes.
So a node will start sending marker, if you receive the first marker.
Yes. After you receive the first marker, you send markers on all processes with whom you have a socket connection.
So the other marker come back will not trigger the marker.
You're saying if J sends a marker to I, the other marker that comes back to you is not going to trigger what?
So the I send marker to J.
Yes.
And J will reply a marker to I.
Yes.
And I will not send a marker.
Okay. So yes, I think that's a good question. So I think that was mentioned here. So if you actually receive the first you have to ensure that you receive a marker. Okay? First marker, and then when you get another marker back, that is simply telling you stop recording. And all you do is stop, you don't resend markers. Okay? The first marker says start recording, any subsequent marker says stop recording. When you do stop recording, you don't send any more markers. You're simply saying I'm done. Okay, so that is basically the reason why you won't keep sending the marker. Otherwise, you'll just have a loop here where you're just sending markers. Okay, yes, question.
what if we have a process that comes up after I send out a marker, but before it receives all the markers in its input channel?
Okay, so the question is what happens if a process starts up and joins the system after a snapshot has been initiated. Okay, this algorithm doesn't handle the case where the n is changing, n is the size of the system. Okay, you can't have scenario where process crashes in the middle of a snapshot, then there are no guarantees. Neither can you handle a scenario where new processes come up. Only in the case where n is fixed over the lifetime of the snapshot algorithm. It can change otherwise. Okay? But once a snapshot starts, you have to work with that end. Okay? You can't have new processes or processes failing. When a process fails, you may never send an outgoing marker, for example. So I may keep recording forever. Okay, so you can't have failures are not handled. Failures won't guarantee termination. System changes are not handled. Okay? Over the course of the snapshot algorithm. So otherwise, you are okay to do all of those things. Any questions here? Okay, so it should be clear that there's a picture from the book that I'm going to show you. Here is whatever I drew here. That's a process queue. That's this disk. Here is this is the incoming socket connection. Those are outgoing socket connection. The first time you receive a marker, you will checkpoint your state. You will send out, as you see, then queue sends out markers on all of these outgoing channels, and it will start recording. So as you'll see, on all of its incoming channels, it start recording until you receive markers on your incoming socket. Same thing just shown in pictures, whatever I drew here. Okay, it's better to actually draw a graph to convince yourself than something like that. That way, you can work out who sends markers to whom and how markers come back, and convince yourself that the algorithm indeed will have every process will capture a snapshot. All messages in transit will also be captured. Okay, so the last question really is whatever packets you are storing on your disk, are those actually messages in transit? Yeah, and we should say yes, and that's because messages in transit are all the messages that are actually have been sent in flight after some process checkpoints its state. Okay, so you basically A is checkpointed its state and C is checkpointed its state at some later point. Any messages that were sent between those two periods are precisely the messages in transit. Okay, so if you look at A checkpointed its state and sent a marker. Okay? And while it's doing that, C is busy sending packets, and as soon as C is checkpointed its state, it sends a marker here. So between these two periods, these are the packets that were sent. Those are the packets in transit. Okay? So it should be clear that any messages that are sent by a process after it's checkpointed a state and sent out markers, but before it receives a marker on the incoming channel, are precisely the messages in transit. And those are the ones that are getting captured. We are assuming, of course, this is TCP, so the message won't hop over some other message, then you will not be able to make this work. Okay, so you're getting in-order delivery of messages. Okay, any other questions here? Okay, so I have argued why this algorithm will terminate, also sort of informally argued why it's actually capturing messages in transit and is going to result in a consistent cut. So the important thing to realize is that different processes in the system are not taking actual snapshots at different points in time. It's not that you basically chose a particular time, all processes froze and they took a snapshot. Okay, we are letting them take snapshots at different points. There's no clock synchronization. Okay? So A will start, B, C will take a snapshot at some later time, E and D will take a snapshot at yet some later time, yet everything is consistent. You can restart the processes from their memory states and by replaying the messages, and they will actually get you the desired property. Okay, so we did not require any clock synchronization here. Yes, your question.
If you have not packed some messages, is that the sender is going to resend them? Why would you have to record the ones that are on the
Question is, if you have not acknowledged the message, will then the sender resend the message? That's your question? Okay. So, and then why are we capturing the message to begin with? Is that the issue? Okay. So, messages in transit could mean any of the following things. Okay? It could mean that the message is queued up in the OS at machine A, but not delivered to the application. It could mean that the message is actually in transit at some router somewhere. It's neither at A nor at C. or it could mean that the message is actually with the operating system of C but hasn't been delivered. Yeah, those are all definitions of messages in transit. Before you actually initiate a send on a socket, those are not messages that are even being sent. Okay, but once you actually do send, the message goes to the OS. Okay? Whether you hack it or not doesn't matter. If the machine crashes and comes back up, all memory contents are lost. Okay? So it's not going to appear suddenly and get resent. So you have to record it somewhere. Okay, so that's really the issue. So when we say transit, we means it's with the OS or it's in the network, but not with the applications. Okay? We are only restarting the application. The OS state may not be present. Whatever is on the network may not get delivered if the machine crashes. So you want to capture them all in order to restart. Any other questions here? Okay. So we'll talk about a variant of snapshot algorithm which is called termination detection. This is actually a very simple algorithm that simply depends on the snapshot algorithm. Okay. So termination detection simply says is the following problem. Assume there are n processes that are performing some computation. Let's say it's a distributed simulation of some sort. Okay. The way they perform computation is they do some local computation, they send messages to other processes. Other processes may receive those messages and perform additional computation based on whatever the messages say. The messages could be RPCs, for example. So if you send RPCs, you will perform computation based on those RPCs. Okay. So now the question is, how are these set of processes to determine as a group that they are actually done with the job that they were running? Okay. Which means the computation that they were running is actually done. Okay, how do you go about figuring that out so that they can all terminate? Okay. And so this is called the problem of termination detection, which is detecting the end of a distributed computation. Okay. So the insight here is if any process still has any local computation that is remaining, the global computation is not done. Okay, because I still have work to do. If I have work to do, then over the course of that work, I may send additional messages to someone else that may trigger additional computation. Okay? So the global computation is done only when each process has finished all of its local computation and every message that is in transit has also been processed. At that point, each local process is done in the system. There are no outstanding messages, so no message can trigger any additional computation, and everyone is done at that point. So you can terminate all of your processes. If any process or any group of processes has any local work to do, we say that the system is still computing, it's not done. If there are any messages that are still in transit, which means they have been sent and not delivered, that can trigger additional computation, so you're still not done. So the question is, how do you go about detecting termination of your system? Okay, so you don't want a human to figure out whether all of this is done. You want the processes to themselves agree whether they're all done or not. Okay? And the way this is actually done is very straightforward. You are simply going to ask every process, collect all the replies, and based on those replies, you are going to figure out if the computation is done or not. Okay, so in this case, we'll assume any process can start termination detection. Say some process says I'm done locally, I have nothing left to do. Okay. So I'm going to check with everyone else to see if they are done. If everyone is done, I'm going to quit, meaning the process will terminate itself, do exit and stop. Okay. But if anyone is yet to finish, then you will keep the process running even though local work is done. Additional messages may come that may trigger yet more local work. Okay. Like more RPCs may arrive, for example. So you will basically ask all your processes. So what you will do is you will do the same kind of algorithm you did in the distributed snapshot. You will send a query on your outgoing channel saying, are you done? Okay. So each process that receives this message will in turn query all of its outgoing channels saying, are you done? Okay. And so on. And then if any process is done and it receives a message from the parent, so it will send back a done message if all its children are done and it is itself done. Okay, so everybody I asked said they were done. I am done, so I'm going to send a done message to whoever asked me first. Okay. On the other hand, if any of my children or their descendants tell me that they are not done, okay, not done in this case just says continue. Continue says I need to continue, I'm not finished. So if anyone says they are not done, I send a continue message back to my parent. Okay, so this is simply a query protocol that's just querying the entire system, all end nodes. It is just going to form a tree. So the root of the tree is the node that started the termination detection algorithm. It sends a query to its children. Those children will send a query to other nodes, and you'll basically form an overlay tree on this system. And then what happens is you wait for responses to come back from your children and its subtree, and then you compare. Everybody is saying done, you are done. You say, okay, everyone in my subtree is finished. If anyone says no, then you basically say no to your parent. So eventually you'll get either a yes, no answer. Everyone will say yes, or if anyone says no, you'll get at least one no. If you get one no, then you basically say time to not, it's not time to stop, time to keep going. Okay, something more may happen. Yeah, this is called the problem of termination detection. It allows processes themselves to figure out whether they should end the entire distributed computation or should the processes keep running. Is that clear? Any questions here? Okay. So that's termination detection. Okay, now we'll talk for the rest of this class, the next half an hour or so. We'll talk about election algorithms. Yeah, it's a different problem. We finished distributed snapshots, talked about termination detection. We are now going to talk about what is called leader election. Okay, so leader election is the problem of having a set of the processes in a distributed system pick one leader to act as the coordinator for something. Okay. So there will be many algorithms that you will have where you need to pick a coordinator. Okay, the coordinator is responsible for some task. So if you think about clock synchronization, okay, you pick the time server. Okay, that is a coordinator, it's coordinating synchronization. Okay. There will be many such scenarios where you need to dynamically pick a coordinator. Okay, you don't want a system administrator to say that is the machine that's going to perform the task of the coordinator. The processes themselves elect a leader. That leader actually performs that task. If the leader fails, you rerun the leader election algorithm, pick a different leader, okay, and that leader takes over those responsibilities. Okay, so that's the basic idea. Okay, so we want to ask the question, how is it that a set of processes can agree on a leader? Okay, so what this means is you cannot throw up two leaders. Okay, that's going to cause some problem. You need one coordinator. Okay. If there is no coordinator left, the coordinator crashes, you need to be able to pick a new one and a unique new one. Okay, so you don't want to have no coordinator or multiple coordinators. You want one coordinator. At the point where the coordinator has failed, there may be a gap where there is no coordinator, but you should be able to rerun the algorithm, choose a new leader. Okay. So this entire class of algorithms is called election algorithms or called leader election algorithms. I'm going to only present three very straightforward techniques to do this. But again, this is an entire area of research and there are dozens and dozens of papers that have been written. If you just go and Google leader election algorithm, you'll see lots of hits. There will be many different variants of how do you decide who is the coordinator based on various different scenarios. Okay. I'm going to present a very straightforward algorithm just to give you the idea of how to do this. Okay. There will be two that I'll present. Then there's a third one that I'm going to show you that derives from one of these two. Okay, so we'll look at what's called the bully algorithm and the ring algorithm. Is the problem clear? Okay, so you will probably use leader election in the next lab where you have to dynamically pick nodes or some processes to perform some tasks. Okay, so these are the kinds of algorithms you may actually have to use. Okay, so the bully algorithm is very straightforward. Okay, so you will assume that processes are numbered. Each process is a unique number, so you'll number the processes 1 to n or 0 to n minus 1 or whatever the numbering scheme may be. Okay, so you'll give an integer ID to each process. How that is done is independent, we will not worry about it. We'll assume each process has an ID. Okay, and then we'll assume that processes know the IDs and addresses of every other process in the system in this case. Okay, so I need to know who are the n processes in the system and I need to know how to communicate with them, which means I need to know their IP addresses and whatnot. Okay, we'll assume that that is also known. Again, how that is known is independent of the algorithm. There may be many ways for you to figure out what are the end processes in the system, what are their IDs, what are their IP addresses. We will not worry about that. This is just initialization. We'll assume when you start, every process is given a unique ID. Every process in the system knows about every other process in the system and their IP addresses for the purposes of leader election. Okay, so I need to communicate with other processes in order to elect a leader, so I need to know how to communicate. For that, I need to know their IP address. Okay. We'll assume communication is reliable, which means we'll assume TCP. No messages are going to be lost. And the basic idea is you have to have some rule to select a leader. We are going to pick the simplest rule, which is pick the ID of the process with the highest ID in the system that's still alive as the leader. You can pick any rule you want. Our rule is going to be of all the end processes, what's the process with the highest ID that's still up? Okay, we are going to select that process the leader. That process goes down, the next highest ID process is going to become the leader. If you want an algorithm to actually make that determination, saying what's the process with the highest ID. Okay? Any process can initiate an election. Okay, if you feel like the coordinator is not responding to you, you can start an election algorithm. So I think the coordinator has failed, let's elect a leader. Okay, and then this process is going to result in a leader being elected. Okay? If a previous leader that failed comes back up, okay, and it feels that it should be the leader because there's a leader with a lower process with a lower ID, that's the leader, and my ID is higher, that process can simply initiate an election algorithm, and if it is indeed the highest ID process, it will win. Okay, and then it will take over as becoming the leader. So any process can start the algorithm. If you feel the coordinator has failed, you can start it. If a previous coordinator comes back up and believes it should be the leader, it can also start the algorithm. Okay. And now the question is, how do you actually figure out what's the process with the highest ID? Okay, I'm not going to show that algorithm for a second. I'm just going to ask, what do you think can be done to figure out what's the process with the highest ID? Yes.
You just broadcast your IDs and send the highest ID, compare your ID to that ID and send the highest one.
Okay. So suggestion is let each process tell everyone else what their ID is. You compare the IDs and figure out. That's a good algorithm. You'll see a variant of that in just a moment. Any other ideas on what you could do? Okay, so you can ask each process what is their ID and then figure out who is the process with the highest ID. Or processes can broadcast their IDs and then everyone else sees who are all the processes that are alive and you pick. Okay. Those are the only two ideas we have. Okay. The way you are going to figure out is you have to ask, okay, or you let everyone tell you. And you'll see the two algorithms are actually variants of these ideas. Okay. So we will basically, our leader election algorithm will have three messages. There's an election message which says let's start an election. There is an OK message which says that I drop out, essentially I'm not going to be a leader. And I1 message is the process message that the leader will send everyone declaring itself to be the new leader or the new coordinator. Okay. The algorithm goes as follows. It's very straightforward. Okay, any process can initiate the election. I'm going to show you pictures and just tell you what is going on. So let's say process I starts the election. So what the process I has to do is to actually figure out if there are processes with ID higher than it that are still alive. If so, one of them is actually going to be the leader. If there are no processes with ID higher than it that are alive, then it is the leader by definition because that's the highest ID process that's alive. Okay. So what process, when any process I starts the leader election algorithm, it needs to send a broadcast to all other processes that have IDs higher than it, saying let's start an election. Okay, so in this case, 4 is going to send a message to 5, 6, and 7, which is actually crashed. Okay, so 7 in this case won't respond, but nevertheless you broadcast to all processes with IDs higher than yourself. Okay. Now, if you receive an election message from some process that has an ID lower than you, okay, you are going to say OK, meaning that I am still alive. Okay, so basically 4 is going to get a OK message from 5, 4 is going to get an OK message from 6, 7 is not going to respond. Okay. So this is going to cause 4 to drop out of the election, saying there is someone with ID higher than me that is alive. Now you figure it out. Okay. So now each process that actually received that message is going to recurse and repeat the same algorithm. Okay, so 5 is going to say, I am going to start an election because 4 sent me a such, let's start an election message. So in this case, 5 is going to send a message to 6 and 7. Okay. 6 will also start an election because it also received the message, but we are not looking at that. Every process that's ID higher than it will start an election. So we'll start with 5 here. So 5 started an election. So what will happen? 7 is not going to respond. 6 will tell 5 saying, okay, so that will cause 5 to actually drop out. So there's at least one process higher than 6 also. Now 6 has received 2 election messages, one from 4, one from 5. So it will start an election. One of these 2 will trigger an election. It will send a message to 7, okay, which is not shown in this picture, but it will actually send a message to 7. 7 is not going to respond. There are no other higher ID processes. So 6 will declare itself to be the leader, saying no one higher than me is responding to me. So I am the new leader. Okay, and it's going to broadcast itself saying I won, or I am the coordinator process message to all processes in the system, and 6 will become the leader. Okay? Very straightforward algorithm. You're simply recursively asking processes higher than yourself if they are alive, and if so, they recursively keep starting elections until there's only one process left, and that process becomes the leader. So you discovered the leader, new leader in this case. Okay. Multiple elections can be in progress. So long as the state of the system is not changing, you will basically end up with the same end result. So just as 4 discovered 7 had crashed and started the election, 1 could have also found that 7 had crashed and started an election. Okay, it doesn't matter because if the state is unchanged over the course of the election, 6 is going to win in both cases. Okay, so that's fine. It basically will converge to the right state. If some process comes up, 7 comes up in the middle, okay, that's okay. It will start an election and it will cause 6 to drop out. Okay, because it will try to query processes higher than it. There are none. It will declare itself the leader. Maybe if this happens right around this time, it will cause 6 to drop out. So essentially, higher ID processes are bullying lower ID processes to drop out of contention. That's why it's called a bully algorithm. That's question there is.
How are the IDs assigned to processes?
Okay, how are the IDs assigned to processes? That is independent of the algorithm. Okay, you can assign them randomly or you can assign them in any way you wish. Okay, there is no choice. So the other important part to keep in mind is here we are assuming all processes are homogeneous, in that they all have adequate resources to perform the tasks of the coordinator. Okay? Most election algorithms will not actually make that assumption. They will try to pick a leader that has sufficient resources. Maybe it's running on a higher end machine, maybe it has more memory, maybe it's less loaded to be the leader. In this case, we do not make that distinction. This is a very straightforward algorithm where we assume any process can assume the role of the leader. So we are simply picking the highest ID process. Okay. You could have basically, instead of IDs, said I'm going to pick the least loaded process. Okay. You could sort of come up with variants of this where you broadcast your load and you make anyone with lower load keep dropping, higher load keep dropping out until you are the process with the least load in the system, you become the coordinator. There are many such variants you can think of. Okay? This is the very simplest one which says, I am not looking at any matrix, resource matrix or anything of that sort. I am simply going to assign some IDs in random order, assume processes are homogeneous, and just simply pick the one with the highest ID. Any questions on this? Okay. So it should be clear that the complexity of this algorithm is O(n) square. Okay, the worst case is when the least ID process starts the election, it's going to send n-1 messages. Then each of these other processes is going to send -2 and -3 messages, and so we'll have order n square messages. Okay, so that's the complexity of this process. This algorithm. Any other questions here before I move on to the next variant? Okay, so now we'll talk about another one which is actually linear complexity, not polynomial. Now, this is called a ring-based election. We will again make the same assumption, which is processes have unique IDs, and we'll also assume that these IDs cause them to be arranged in a logical ring. A logical ring simply says if I have ID I have two neighbors, I minus 1 and I plus 1. I can communicate with only two processes in the system, one where that's ID lower than me, one that has ID higher than me. In the previous case, each process had to communicate or had the ability to communicate with every other process in the system. Here you need to only communicate with the node with the ID immediately higher than you and lower than you. If your neighbor crashes, then you have to communicate with your neighbor's neighbor. Okay, but other than that, you don't need to communicate with every node in the system. Okay, so we'll assume processes are unique IDs. They are arranged in a logical ring, and you know your IDs of your neighbors. Okay? Now again, like before, any process can start an election. Okay? And the way you are going to do this is you are going to take your ID, you are going to put it in a packet, and you are going to send it to your neighbor. Okay, the algorithm, you can send it clockwise to your higher neighbor or you can send anti-clockwise to your lower neighbor. Doesn't matter. Okay, you send it along a ring. So these are the same processes as before. 7 has crashed, so basically you are going to assume you need to pick a new leader. So here what is being shown is actually there are two elections that start up simultaneously. 5 notices the coordinator has crashes and starts an election. 2 notices that the coordinator has crashed also starts an election. And what your election message is, you simply add your ID and you keep sending it along until the message actually goes around the ring and comes back to you. Okay, so 2 is going to add its ID saying I am alive, sends it to 3. 3 is going to add its ID saying I am alive. So you have 2 and 3 on the message and you send it to 4. 4 will add it, so it will become 2, 3, 4. So it's going to circulate around and come back. So you will see that this message here that started from 5 has reached 1, it has ID is 560. So each process adds its ID. Okay, so the process that initiated the election, once the message comes back to you, you just look at all the IDs, you pick the one with the highest ID and say that's the new leader. Okay, very straightforward. That was exactly what was suggested earlier, saying you just ask. Everyone tells you their ID, you compare, and then that's it, you're done. Okay, the only part here is 6 needs to know that 7 is crashed, so it sends that election message to 0, which is your neighbor's neighbor. Okay, that is always done in a logical ring. Whenever your neighbor crashes, the ring will no longer be a ring. Okay, it will become a chain. So to re-establish the ring, you have to form a connection to your neighbor's neighbor. Okay, so you'll basically hop over 5 and 6 will send directly to 0. Okay, other than that subtlety, the algorithm is very straightforward. Okay, so the messages will circulate once around the ring, and once they come back to the process that initiated the algorithm, you pick the leader and then you circulate the leader again. So you send another message around the link saying, in this case, you will say 6 is the new leader. Okay. So there are 2 n-1 messages that are going to go around. First n-1 is to ask everyone for their IDs. The other n-1 is to announce the results of the election. Okay, linear complexity. Of course, multiple elections can be in progress. Each election takes order of n messages. Any questions on this? Okay, straightforward algorithm. So this is the comparison that I said. In the ring, your 2 n-1 messages. In the Bully algorithm, it depends on who starts. Okay, the worst case is the one with the lowest ID starts, that's order n² messages. The best case is the process with the highest ID that's still alive starts the election, saying the coordinator has crashed and there's no one to query, so it just sends I1 messages to everyone. Okay, so that's basically the worst case and the best case. Questions on this? Yes.
Won't ring also the worst case of n², in case everybody starts an election?
Okay, so this is basically for a single election. Okay? In either of these cases, since anyone has the right to start an election, multiple elections may start up whenever there are failures. Okay? Each election may incur this overhead. Okay? Now it all depends on how you code up your algorithm. So maybe what you do is First time you detect that the coordinator has failed, you pick a random time and you wait for that random time to see if someone else starts the election. That way you will not have a rush where everyone suddenly discovers that the coordinator has failed and there are any elections in progress, wasting all sorts of overhead. So if you pick different random numbers, somebody will start, and if you hear the election, you can just discard the fact that you wanted to also start an election. So you can just use some simple heuristics like that to prevent needless elections, but you can have a scenario where multiple elections may start. Each of them will incur that overhead. Okay. Is that clear? Any questions here? Yes.
Is the ring-based algorithm the election of the leader always based on the ID?
Okay. The question in the ring-based algorithm is the election of the leader always based on ID? The simplest case is you can pick the process with the highest ID. Okay? But as I said, the actual election could depend on any metric. You can send a query to every process saying, give me your ID and tell me your load. Give me your ID and tell me your bandwidth. So tell me your machine configuration, and you can pick the process with the least load and pick the process with the most resources. And there are many other variants of it. This one just says you pick the highest ID process. That's the simplest one. But you could vary it easily to do other things.
But what if on the fly the load decreases or increases for a particular?
Yes, so you could of course have dynamics in the system where the load may change, so you can ask for load history. There are any number of techniques you can think of, and probably you'll find a paper that did exactly that. That's why I said there are dozens and dozens of papers, because it's okay, tell me your load of average over the past 10 days or 10 hours, and I'm going to pick the one that has the least minimum load over time rather than an instantaneous load. So there are many scenarios you could pick, and that will give you a variant of this algorithm. Okay, so that basically, so I'm going to give you some scenarios which are similar to what we're being asked. So there are often leader elections being done in wireless environments, and then you can use channel characteristics. I have the best reception, or I have the most channel bandwidth, because channels may be congested. So you don't have to pick based on ID, but you can pick based on channel characteristics. That's an example. I'm not going to go into this algorithm, which is sort of like the some of the variants we have looked at. There's an example in the book, but I'll ignore that for now. Okay? Instead, I'll talk a little bit about how Skype performs leader election. Okay? So in this case, if you remember when I was talking about Skype in the context of peer-to-peer systems, I said that in Skype it's not a pure peer-to-peer system, it's a hybrid where there are super peers. Okay? Each super peer manages a group of peers, and the super peer is responsible for tracking which peers are up, what users are logged in, what is their status online, offline, and so on and so forth. Okay, so the question is, how do you go about figuring out who a super peer is? Skype actually runs a leader election to do this. Okay? But in Skype, you are not going to simply just compare IP addresses and say you have the highest IP address in the group, so you become the leader. They don't do that. They actually look at various metrics. So, for example, you assume that you have low latency access to the super peer. You want the super peers to be evenly distributed across the network. If you assume that your Skype P2P network is some sort of a graph, you want even distribution so that the number of hops to some node is always small. So your nearest super peer is small. So you want even distribution. You want good resources. Okay, there should also be a fixed number of super peers. Okay. So what that also means is how you form the groups, and then within each group you form a peer is also determined dynamically. So when you log into Skype, you are going to join some cluster that already exists, and you want the sizes of cluster to be relatively the same. It needs to grow. You can't have one cluster where there are lots of nodes, and another cluster there are few nodes, and some super peers will become heavily loaded and so on. Okay? Keep in mind that this is not electing a single leader. Rather, you are electing one leader in each group. That's a super peer. There will be many super peers in your network. Okay, so each group is going to run a leader election algorithm to elect a peer within the group. That is that becomes a super peer. Okay. So you may occasionally notice, if you actually pay any attention and your Skype running in the background, that suddenly there is more traffic to your machine. Okay, even though you don't seem to be doing anything, these may be scenarios where Skype has decided that your client actually becomes a super peer. Okay, so if you are a super peer, you have to answer more queries, because every time somebody in your group logs in or changes their status, they have to inform you, the super peer, and the super peer tracks status of all of the nodes, their IP addresses, and so on and so forth. Okay, so that's basically the Skype problem. So in this case, you try to pick nodes that are relatively on faster networks. Okay? If you are on a cell phone and you are doing Skype, you don't want to become a super peer and have your super peer start using up your cellular bandwidth, for which you may have a limited amount of quota, for example. Okay? But if you are in a fast LAN, there's plenty of bandwidth, that's acceptable. Same as the load on the machine. If your machine is heavily loaded, you don't want Skype to add to your load. Okay? So you will actually take all these issues into account. Okay? In addition to all these other issues, the super peers need to be evenly distributed. You don't want all the super peers to be in United States and Europe, because everyone has broadband connections, but other continents connectivity is poor, so you don't put super peers. Then there will be long latencies to get to your super peer. That's also not a good thing. Okay, so even distribution of super peers, even sizes of groups that each super peer manages, making sure the peer has good available resources. All of these are considerations in the leader election. Now, the leader election that Skype uses is actually not published. At least to my knowledge, it's not published. So I don't know exactly what they do, but based on what we have looked at so far and these considerations, it should give you some sense of how it might work. That's just one example of leader election. In practice, of course, this is a very common problem. So you see leader election coming up in many different scenarios. Okay. Questions here? So I'm going to go for the last 10 minutes talk about this problem of distributed synchronization. And we're switching topics again. This is yet another problem in distributed system. This is the problem of implementing a distributed lock. So we'll assume there are n processes in the system. They are running on different machines. Let's say they access some shared variable. It could be a shared file, doesn't matter, some shared data structure. And you want to use lock so that two processes don't write to the file at the same time. The file may be on a third machine. Okay. So how do you implement this notion of a lock? If you are writing multi-threaded application, the lock is part of the same process. Okay. All the threads compete for the lock. One process gets the lock, it does whatever it needs to do, it releases the lock, the next process gets the lock, and so on. You want to have the same concept, but now you want to generalize it across machines. Okay, so the processes should somehow coordinate with one another, okay, and pick one of these processes that wants to acquire the lock, is given the go-ahead, so it assumes that it holds the lock, it does whatever it needs to do, and it yields the lock to another process, and so on. Okay. Question is, how do you actually go about implementing this? So we want to basically have a locking mechanism for a distributed environment. Okay. Simplest approach is going to be, we'll make the lock, although the environment is distributed, the lock can be centralized. Okay. And then we'll see how to make the lock really distributed. Okay. So centralized locking is straightforward. I'm going to just talk about that and then maybe I'll end. So again, we'll assume processes are numbered. Okay. We'll assume that you basically run a leader election and pick a lock coordinator. Okay, we know how to do leader election now. Okay, so we'll pick one process in the system saying you are the process that's going to coordinate the lock. Any process that needs the lock is going to ask you for it and you figure out who gets the lock. Okay, so this is centralized approach, so we pick a coordinator. That's the one that is going to manage the lock. Okay, so every process needs to deal with the coordinator and ask for the lock. Okay. So if you need to grab the lock to get exclusive access, you are going to send a request to the coordinator and wait for the reply. Okay. If the lock is in use, the coordinator will wait to send you a reply. So you will be blocked exactly the way you are blocked on a lock. So if you do lock acquire, if the lock is on use, you will block. Okay. Same thing will happen here. You will basically, instead of doing lock acquire, your lock acquire may be an RPC. That RPC message will go to the coordinator. If the lock is in use, the coordinator will delay a reply until the lock is in use. Okay? If the lock is free, you will immediately get a reply saying go ahead. And then you basically can assume you hold the lock and do whatever it is that you're doing. Okay? And of course, when you're done with the lock, you have to then release the lock. Okay? Coordinator is very straightforward. When you receive a request for a lock or a lock acquire, if it's available, okay, you basically grant the lock. Okay, if it's not available, then you queue the request. Okay, so, and then when you do release, you're going to send the queue. So here is the picture that shows exactly that. 4 processes, 0 to 3, run leader election. 3 becomes the coordinator based on our algorithm. It picks the highest ID process. That's the lock coordinator. Okay, so it maintains a queue. So here is a case where you basically initially one requests the lock. Okay, so it gets an OK, so you have the lock. So it keeps track that the lock is now in use. If 2 makes a request, okay, that request is put in the queue here. Okay, you're not going to reply. Okay, you're going to wait for 1 to release the lock. At which point you look at the queue saying, is there outstanding acquire messages? If so, you take one of them and do a OK to that message. That's what has happened. Okay, so 2 is going to block in this case until 1 has released the message in the next time step, at which case you get the lock. Okay, so you're ignoring some details, but this is the basic algorithm. Okay, so this is a centralized coordinator. So you have to ask all sorts of questions. Why will this work? What happens if the coordinator crashes? Okay, you'll pick a new coordinator. You can always run leader election. But how does that coordinator know what is the state of the lock? Who holds the lock? Because the previous coordinator is gone. Okay, so what that also tells you is the state of the lock better be persistent across process crashes. So you can keep the state in a file somewhere. Okay? You can replicate the file or do something so that if the coordinator crashes, you pick a new coordinator. If the coordinator comes up, it doesn't know what the current state of the system is. Is somebody holding the lock? Are there processes queued up? If you don't know that, you can't resume from where you left off. Okay, so anything you're doing with the lock, you better also keep a copy of whatever the current status is on a disk. You put some information in a file that some other process can read and know what happened. Okay, so you have to make all of these decisions. Okay. The worst case is client crashes. Okay. You give a lock to one. Okay. One is holding the lock and one has crashed. That's a hard case. Okay. You can't just take the lock back. That kind of stuff does you. Locks have to be released. You cannot just forcibly take a lock back. Because how do you know if one is going to restart and just continue from that point on? Maybe some user will restart. If you took the lock back and one restarts, it still assumes it's holding the lock, then there is a problem. Okay. So now if a client crashes, okay, your lock may be held forever. You don't know what to do. If it's a real crash, you can't just take it back. Okay, so dealing with failures is a thorny problem. In a multi-threaded application, okay, typically if process crashes, everything is gone. All the threads are gone. Okay, so that's a simpler problem to deal with because there is no coordinator. No other threads can make a request if all threads disappear. The process itself crashes because of a bug or a failure. In this case, these are processes running on independent machines. So it's entirely conceivable one process that holds the lock will crash. There's a bug or something goes wrong, and then the coordinator is waiting for that lock to be released. You can't enforce a time limit on a lock. You can't take back the lock. The standard definition is processes that are acquired the lock will release it in the future. If that assumption is no longer true because of failures, this process will not work. The centralized coordinator will no longer work. Okay, so dealing with failures is a big issue here. That's something we'll have to keep in mind. Any questions here? Okay, so there's a distributed version of this algorithm. It will take a little time to explain, which I'm not going to do right now. We have run out of time. So we'll stop here for today. Okay. There's no class on Wednesday. There's an exam on Wednesday evening, but there's no class. Okay. There's no point having a class. You'll all be distracted. So instead, I'm going to have office hours. You can come ask me questions about the test material. Okay.